Good afternoon, everybody. Hope you're having a good day.
Put something a little louder for the camera.
Okay. Yeah. You will have to talk a little louder. So I have the thing set at 10 plus 10 decibels, which is going to help us out a lot as far as, so I can back away like this. Now, this first set we're going to look at is 21 through 24. And it says graph the function, tell whether or not it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it is removable or non-removable. And from the video that I showed you yesterday, remember that part 2 video, I think, and there was part 1, talked about all this. And so I understand how you might not remember everything at this point. Is there anybody who really knows how to do this right now, right off the bat? Maybe a little bit. Well, what I suggest doing is we're going to go back here in history to problem 13. Okay, this is problem 13 that was worked out in class a couple days ago. You remember this one? And what I ask you right now, can you tell if there's a point of discontinuity where x equals 0 based on what you see here? No?
Yes, because there's 3 different points, or 3 different little unions.
Yeah, so x cannot equal 0, so this is evidence of point of discontinuity. All right, now what I want you to do is graph this function in your calculator.
Oh, you don't?
And while you do that, I'm going to likewise do it. So I go over here and put x over x squared minus 5x, is that it? So we graph the function and this is what we see, right? So graphically, do you see any discontinuities here? Where do you see a discontinuity here?
0 and 5.
0 and 5. Okay, now the 5 we can see really well, right? That's this thing right here. This break at x equals 5. And break, right, synonymous with discontinuity. What kind of discontinuity would we call this?
Hold on, I have it in her notes.
Yeah, we think she has in her notes.
Vertical.
Okay, that's part of it. Part of it, vertical what? Okay, vertical asymptote.
That's what I said.
Okay, vertical asymptote. And what other kind of, what else do we call this thing? Starts with an I.
You were wearing the shirt.
Isosceles.
Okay, we call it infinite discontinuity. Okay, infinite discontinuity, vertical asymptote, and also what do we call this? Now, if you look at problems 21 through 24, what it says, instructions, we call this, and it was on this shirt I had last week, or earlier this week, called a non-removable discontinuity. Okay, now, so we can see that right here. Now, Adam also mentioned that we have a discontinuity at x equals 0. Now, when you look at this graph, can you see a discontinuity of x equals 0 here?
Yes, but barely.
But it looks like you might be able to make out something here,
You
right?
have to look at the table to see if it says error.
Yeah, so let's go look at the table. Let's do that. Okay. So we go to second graph, and we can see at x equals 0, we have an error. So here we have, with the calculator, evidence of a break or a discontinuity. All right, now, we already know at x equals 5, we know that that's a non-removable discontinuity, vertical asymptote, or infinite discontinuity, right? Just 3 synonyms of saying the same thing. what other types of discontinuities are there? I don't know if you remember the shirt I had. There are two other kinds that we talked about.
Horizontal.
Okay, well, horizontal would be horizontal asymptote could be a discontinuity in range. But normally when we talk about discontinuities, we're talking about breaks in the domain.
Jump?
Jump discontinuity is another type of discontinuity. Okay, so let's just file that away. And one more kind of discontinuity.
Continuous? Or that's,
One other type of discontinuity. Now, you guys make sure you stay off your phones, right? Thank you.
I'm looking at them.
Okay. What other type of discontinuity besides, so we have the infinite discontinuity, the jump discontinuity, and lastly, well, yeah, removable. Okay, that's one thing. So that other type of discontinuity is removable and has two other names. One is a four-letter word, starts with an H. Okay, it's called a hole. Okay, so it's like a dot, it's like a point, but empty in the middle. That's a hole, or a point discontinuity. And what happens is, we already saw that x equals 5, there is an infinite discontinuity, right? Or non-removable discontinuity. But can we rewrite this g of x in factored form? Let's rewrite this in factored form. So what's the factored form in the denominator? And what can we do now? Cancellation, right? And what we've done now is algebraically we removed it by canceling. And if you can remove by a discontinuity by cancellation, that makes it a removable discontinuity. And by appearance, we don't see anything at all. Now, Adam pointed out that it looks like TI might have been able to do something to make it barely visible. But normally when you graph, you're not going to see it, okay? It's going to, because the function is defined all the way up to 0 and all the way after 0. Now, I want to go ahead and type in what the removable with the discontinuity removed. We have 1 over x minus 5. What is this going to look like? It typed right over, went right over, right? But now we go to the table view, what are we going to notice?
0.
Okay, here with the discontinuity removed, the function is defined, where the discontinuity is not removed, but in all other respects, the function is identical, right? Or at least the output of the function is identical. Okay, so that's, I just want to go over that before we go directly into problems 21 through 24, where we now go, okay? So here we graph the function, tell whether or not it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it is removable or non-removable. So now we come here, and it says graph the function. So if we graph this function, and I hope you have your calculators for this, we graph this function, what do we see?
Pretty much the same thing you're saying. But into
Yeah, it's the same one as that problem 13, except in a different place. So do we have a point of discontinuity at x equals 0?
Yeah.
Yes.
Yes. And if so, tell whether that discontinuity is removable or non-removable.
Non-removable.
Non-removable. Okay, Adam or anybody else, how did you tell that that is a non-removable discontinuity? Okay, so Kinsey makes a, you can't see anything to cancel, right? Okay, so that's one thing. And what else? Well, the one reason is that an infinite discontinuity or a vertical asymptote is synonymous with non-removable. So you just see that. And so what I've done, and I did this with my discontinuities t-shirt, is just by association. Okay, vertical asymptote, infinite discontinuity, and non-removable. Is just to associate these things mentally together. They are synonymous. Okay, well, the vertical asymptote is a result of it being a infinite discontinuity, essentially. Okay, let's go on to, any questions on 21? Let's go on to 22. On 22, okay, before you even graph this, it says graph, but before you graph it, is there a point of discontinuity at x equals 0?
Yes.
Yes. How do you know this without graphing? Without graphing, you look at it, you know there's a point of discontinuity at x equals 0. Why is that? Because what happens if x is 0?
Just when it's discussing.
And why do you have a point of discontinuity at x equals 0? Because what is there strange or unique about the property of
Cannot divide by 0.
there? That's it. You cannot divide by 0. So if x is 0, you see function's undefined. Boom. So the answer to the question is yes, right? So we do that even before we graph. And when we graph, and I'm assuming by this point that you've already graphed the function in the calculator, and when you graph this function in the calculator, you're going to see something like this, right? So now we've graphed it, and is this a removable or non-removable discontinuity?
Removable.
Removable. And how did you know this was a removable discontinuity?
Because it cancels out the x.
Okay, and we haven't done that. So we can cancel out the x? Well, let's try that out. Let's rewrite h of x. How do we do that? So we put this x down here. What do we do up on top here? What is your common factor up here?
X.
X, right? So it's x, and then
X squared.
x squared plus 1. So what does the graph of this function look like? Exactly like that, right? Looks exactly the same. But we know we're going to get an error when we enter the original function in. Okay? So, are you okay on this, Em? What's going on? Any Carbon, you okay? All right. Let's go on to number 23. Now, 23 is, what do we call that in the numerator?
Absolute.
An absolute value. And did we in Algebra 2 Honors last year learn how to put this in our calculator? Yes, we did.
I don't remember.
Yes, we did. We don't remember. This is one of those obscure things that's hard to remember. So what I want to do,
It's up in the
Math, number, and I'm pretty sure absolute values at the top.
math, number, absolute value. So that's a go-to way, one way. I'm going to examine that way. So I'm going to pick Adam's way first. I'll show you another way too. But let's.
do alphabet.
So if we go to
Math,
math, number, and just press enter.
yeah.
So that's one way to get it. I want to show you another way too, is you can go to second, catalog, enter. get the same thing. So we get x, absolute value of x over x. And then we graph the function. This is what we get. Okay? What kind of discontinuity do you think this might be?
Jump.
That is a jump discontinuity. And this, using an absolute value, is the only way I can think of algebraically to make this to make it work out. So we call this yes, right? Is this a removable or non-removable discontinuity? Non-removable. And you can kind of think through this thing, like if to the left of the y-axis, is the numerator ever going to be negative? No. Is the denominator ever going to be negative? Yes. And where is the denominator negative? Where x is negative. So denominator is negative, and what happens all of a sudden at after x equals 0? Yeah, so we have a positive over a positive here, and we have a positive over a negative to the left of the y-axis. Any questions on 23? Okay, now for 24, do we have says graph and have a,
There's no discontinuity.
so no discontinuity at x equals 0?
No.
So if we put x over x minus 2, my thinking is we have something that looks like this. Is that right? And then something that looks like this. Is that right? Okay, so that's the graph of that. So no. And if there is a discontinuity, is this removable or not removable? Well, that's,
No.
yeah, there's no discontinuity. So we can't answer the question. If the answer is no, we can't answer the question any further. And what, at x equals 2, what kind of discontinuity is that?
Non-removable.
Non-removable, which is synonymous with,
Got the word.
What was the question?
okay, Adam said this is a non-removable discontinuity. He's right. What other things can we call this besides
Infinite discontinuity.
infinite discontinuity or a
Oh,
hole? No. Vertical asymptote, okay? Let's go on here. 25 through 28 state whether each labeled point identifies a local minimum, a local maximum, or neither. Identify intervals on which the function is increasing or decreasing. And in the lecture videos that we watched a little bit yesterday, in the part 1 and part 2, did cover all this, didn't it? You remember that? Okay, let's go ahead and talk about this. So this one right here at -1, 4, is that a local maximum, local minimum, or neither?
no.
Local maximum.
Oh, yeah.
Local minima equal valleys. Okay, so we have local max here. What do we have down here? Local minimum. What do we have here at 5.5?
Local max.
Now, next it says identify intervals over which the function is increasing and decreasing. So we say, I'm going to abbreviate a little bit. This is one thing you're going to get used to the rest of precalculus and calculus. So we say the function is increasing on, and when you just say increasing on, that is a shorthand for on the interval of. Okay? So where is this function increasing?
From negative infinity to
What did you say?
negative infinity to negative 1/4 or 4.
So it looked like, so Adam was very certain on this, right? But now he's trying to think what number goes net, negative 1 or 4?
Negative 1.
Negative 1? Well, that's right. But why negative 1 and not 4?
Because it's the x.
Okay, the x value, how do you know the x value is
The x
4?
is always put first.
Yeah, well, what it is when you say where, or so which numbers, if you look over there by Emily, see where it says that we have the where what, right? The where is horizontal. And so you're looking at x values for intervals. And that's a point, because on tests and so forth, a test writer will say, is the function increasing from negative infinity to 4? Well, yeah, but when you talk about functions, you are most of the time talking about the x values where something is happening. So Adam is right about that. Where else is the function increasing?
2 to 5.
So increasing from x equals 2 to x equals 5, right? Now, I put parentheses here. Could I use brackets instead?
Yes.
I can't use brackets with the negative infinity, but I could possibly use brackets elsewhere. And the reason is because the thing is increasing all the way up to and including 5, because there's nothing left to the there's nothing to the right of that, because the function is decreasing after the right, so the function's increasing all the way up to. So sometimes you'll see it written with brackets. That's something on tests. I'm not going to beat you up over that, nor does AP test. Anyway, where are we decreasing on this thing?
Negative 1, 2.
So negative 1 to 2. Anywhere else?
5 to infinity.
So 5 to infinity. Okay, so those would be our answers for this one. Questions on this one? Okay, let's go on to 26. Okay, 1, 2, min, max, neither.
Minimum.
So local. Is there another word that we can use instead of local?
Yes.
Relative. Yes, ain't it? Relative. So local minimum, relative minimum, synonymous. Okay. 3, 3, min, max, neither. 5, 7. Local or relative maximum. Okay, so now what are the intervals? Where are we increasing?
1, 5.
1, 5. Now, sometimes you'll see things broken up, like somebody might say, well, looks like we're flattening out at 3, so it might say 1 to 3 and then 3 to 5. But if you look at it, even if the thing flattens out perfectly, still the function is increasing over that entire interval. Okay, so that's the way I would write it. Okay, and where are we decreasing?
Negative infinity to 1.
1. And where else? Anywhere else?
5 to
5 to infinity. And I don't know if you did this when you were writing your answers down, but you can kind of check to see if the function is increasing, decreasing, you ought to be able to fit this piece in between these two, right? So what do you have to be able to fit this in nicely? These numbers to be the same, right? So just something to watch out for. Okay, 27. This one on the left. Is that a minimum or maximum? What about the 1, 5?
That's the max.
And 3, 3?
Local minimum.
Neither. And then 5, column 1,
Oh wait, no, jumping ahead.
local minimum. And where are we increasing on? And anywhere else?
5 to infinity.
And where are we decreasing? Okay. All right. Okay, on to this one here. This one down here at negative 1, 1, minimum. And then at 1, 6,
Max.
yeah, that's a local max. Now, it's kind of weird because it really is not strictly a peak, is it? But it is the highest point either if you go to the right, which does not exist, or to the left. So I would call that a kind of a different type of local maximum. What about down here at 3, 1? And then at 5, 4? Local maximum. Why is this a local maximum here?
Because of the peak.
Yeah, it's a peak, right? It's the highest all around. So local maximum means that you just focus in on this portion, and you see that 5, 4 is the highest point in that smaller piece. Now, if this also happened to be the highest point for the whole entirety of the function, that would also be a global or absolute maximum. Okay, let's see, increasing on, where's the function increasing?
3 to 5.
Negative 1 to 1.
So negative 1 to 1. Anywhere else?
3 to 5.
3 to 5. Anywhere else? That's going to be it, right? So where are we decreasing here? Negative infinity. I mean, if we assume that this thing is continuous, probably a good assumption. Negative infinity to negative 1. And where else? 1 to 3. And one last place.
5 to infinity.
And beyond.
Okay, So that's 28. Okay, 29 through 34, graph the function, identify intervals, which function is increasing, decreasing, or constant. And we in this set today, we're going to just try to do the first 29 and 30. We're probably going to pick up on the rest of these next week. So my recommendation is, now, do you remember working on problems like this last year in Algebra 2 Honors?
A little bit.
Yeah. So you can put this in the calculator, and if you do that, that's fine. While you do that in the calculator, I'm going to pretend like I remember something from Algebra 2 Honors last year. Now, why do you think I might remember Algebra 2 Honors better than a lot of you from last year? Because I taught it, and I had how many sections of it? 3 sections. All right, and I made the videos on all these, but you're talking about an absolute value function, parent function, and the absolute value parent function looks something like this, if you remember, right? You remember that? And so what is the translation according to this thing here? So how many to the left? 2 to the left, okay? All right. That's good. Yeah, so we're going to go 2 to the left, 1, 2, and 1 down. So here it's 2 to the left, so this happens at 2. So let's say we're trying to find intervals where the function is increasing, decreasing, or constant, right? So is this function decreasing on an interval?
Negative.
Negative infinity to negative 2, and increasing on which interval?
Isn't it supposed to be the other way? Then in calculator, and the point is on the 2.
Let's look at this. Always helps to look at the calculator, right? So we go to absolute value. We'll put x plus 2 right here, right? On the outside of it, we would put minus 1, right? So is that right? So we graph, and here the way I have it marked, I have these marked by 1s. So the function's decreasing all the way to x equals negative 2. So that's right, isn't it? Then increasing greater than negative 2. And if I go to zoom square, we're going to see it. We're going to see a more